Hello guys and gals. Welcome back to our next video on kinetics. So in the last section, we stopped talking about collision theory and requirements for a reaction to happen. In this section, we're going to start talking about reaction rates. We're going to look at 5.1. Now, what AP wants you to be able to do by the end of 5.1 is explain the relationship between the rate of a chemical reaction and experimental parameters. Experimental parameters means concentration, pressure, temperature, pretty much anything that you can do to affect a reaction, okay? But in this video, we're just going to focus on 5.1a, which is basically just getting us used to what is a reaction rate, okay? So a reaction rate is measured by the decrease in the concentration of our reactants or by the increase in the concentration of our products per unit of time. So basically what we're doing is saying how quickly are our reactants being turned into our products. This is the equation that we see for that. Rate is equal to the change in concentration over time. So we're just looking at how is our concentration changing per unit of time. We can't discuss this like speed, like there's no distance being covered here, right? So instead of having our distance per time like we would with speed, we have the rate, which is the change in our concentration per unit of time. It's important to note right here that reaction rates are not constant throughout the reaction, okay? Reactions tend to happen really fast at the beginning and they slow down as we get closer and closer and closer to losing all of our reactants. So if we want to, we can look at it like this. If we start a reaction with, let's say, start a reaction with 10 moles of reactants, 9, 10, okay. Well, then two of them collide and they are now not reactants anymore. Now they're products. Well, here's the thing. Products are not the things doing the reacting. They're not reacting at all. So I don't really care that I've made a product. What I care about now is I only have 8 moles of reactant left. And if we go back to collision theory, we can think about the fact that particles have to collide in order for a reaction to occur. Well, obviously, the more particles you have, the more collisions that are occurring. So as the reaction occurs and you keep colliding all of your reactants, you're going to decrease your number of particles capable of reacting. And so therefore your rate is going to decrease as well. Your concentration decreases over time, and so your rate decreases over time, okay? So reaction rates are not constant. You could take a reaction rate every 10th of a second in a reaction and get a different number every time. And so because of that, there are several types of reactions or reaction rates that you can have. And so we're going to talk about that in this section. So in this section, we're just going to introduce the types of reaction rates, and we'll go into a couple of them. For the most part, we're just going to look at an overview. If I can get my computer to move. There we go. Okay. So first things first, we can have the rate of disappearance. How quickly is your reactant being used up? We can look at rate by looking at the rate of how our reactant concentration is changing. Or we can look at rate of appearance. How quickly are my products being made? Now, a lot of people really like to talk about it that way because in industry, if you're trying to sell ammonia, you want to know how fast you're making your ammonia, right? The faster you can make ammonia, the more of it you can make, and the faster you can sell it, the more money you can make, right? But most of the time, we're actually going to talk about the rate of disappearance in chemistry. Now, both of those ideas are called relative reaction rates. Relative reaction rates are when you look at the rate of something using the stoichiometric coefficients from your balanced chemical equation. They don't have to be relative reaction rates, but they are the relative reaction rates when we're talking about relative reaction rates. We'll talk about that more at a later point in time. We also have the instantaneous rate of reaction. That's the rate at a specific point in time, okay? So what was the rate of the reaction 200 seconds after it started? Or what was the rate of the reaction when the concentration of hydrogen was 0.2 molar? So instantaneous rate of reaction is actually what we're going to work with most of the time, okay? I would say, like, if you're going to solve for rate, 99% of the time you're going to be solving for the instantaneous rate of reaction, okay? Average rate of reaction, in all honesty, we don't see it very much because it really doesn't give us a lot of information about what's happening at the molecular level. It tells us how quickly the whole thing happened, but since we know that the reaction rate changed literally every couple of nanoseconds, it doesn't really give us a lot of information beyond that. Now, I included two other pieces of information here that are technically not types of reaction rates, but it's a way to express it or solve for it. So we have the differential rate law, or just regular rate law, which is an equation used to show how the reactants affect the rate of the overall reaction. It shows the relationship between concentration and rate. We also have the integrated rate law, which is similar to the differential, except it shows us the relationship between the concentration of our reactants and the time that the reaction is going through, okay? So we're just going to discuss a couple of these in more detail. First of all is instantaneous rate, because that's the one that we're going to use the most often, but it's also pretty self-explanatory. You're just looking at the rate at one point in time. Now, if you're like me, you're taking a look at this equation right here and you're saying, how can you have a change in concentration if you're looking at one point in time? Can't have a change in an instant. Like, it doesn't work that way. Well, the fact is we're not looking for the change of a rate at this point. We're going to use that differentiated rate law to solve for rate at an instantaneous point, which we'll talk about in a later time. The average rate of the reaction, you literally just take this equation that we've seen in this whole video, and that's how you solve for it. Again, you're not going to do this very often, okay? We'll go into the rest of these types of reaction rates in later videos, but I hope this helped explain some things, and let me know if you have any questions.